Come back. Good news for everyone. GATE admit card has released and NET exam has also announced. But obviously this time is very difficult time because we are going to very difficult condition for COVID. Those students whose exam center has far away from the center, this news obviously very difficult because this time train journey is very difficult. But thank you for everything. Then it will be more easier to take everything easily. And don't want world will be changed. Just keep accepting everything and expect less from others. And keep learning, keep improving yourself. Keep write your goal as a note paper and focus on your goal. All will be good. In my earlier video, I had discussed about prime ideal and number of ideal. Today, at first I will say number of prime ideal of this ring. I had seen in my earlier video number of ideal of this ring. We all of us know, since Q and C are both filled, the number of ideal in Q cross C would be 0 cross 0, I1, I2 would be 0 cross C, I3 Q cross 0 and I4 Q cross C. There is this 4 ideal, and I had discussed elaborately this part in my earlier video. Today's question is number of prime ideal. I1 be not prime ideal because if we consider A equal to 1 0 and B equal to 0 1, then their product AB equal to 1 0 times 0 1 would be 0 0. That means AB belongs to I1, but neither A belongs to I1 nor B belongs to I1. So, I1 not be prime ideal. Similarly, Q cross C not be prime ideal because this is the whole ring. This is not definition of prime ideal. Prime ideal always be proper subset. Now consider I2 and I3. To check I2, consider X equal to arbitrary element AB belongs to Q cross C and also Y equal to CD be the member of Q cross C. Okay? Consider their product B belongs to I2. That means AB times CD belongs to I2, which implies ACBD belongs to I2. And since I2 means the ideal generated by 0 cross C, that implies AC equal to 0 and AC equal to 0 means obviously either A equal to 0 or C equal to 0. And here I have got either A equal to 0 or C equal to 0. That means value of X would be 0B, which belongs to I2 because I2 equal to ideal generated by 0 cross C. Similarly, if we put C equal to 0, then Y equal to 0D. Similarly, this is also belongs to I2. That means I2B prime ideal, because I have got if product of two element belongs to I2, then either x belongs to I2 or y belongs to I2. Similarly, I3 be also prime ideal of this ring. That means there exist only two prime ideal. This is I2 and I3. Means the ring R equal to Q cross C has two prime ideal. Are you getting? Consider R equal to Z7 cross R cross Q. I had discussed in my earlier video type of ideal. There exist 8 ideal. 0 cross 0 cross 0. I2 would be 0 cross Q. I3 would be 0 cross R cross 0. I4 would be Z7 0 cross 0 cross 0. I5 would be 0 cross R cross Q. I6 would be Z7 cross 0 cross Q. And I7 would be Z7 cross R cross 0 and I8 would be whole ring. At first I will highly recommend you, if you don't see my earlier video, please see at first my earlier video. Then today's video would be so easy. This type of ideal I had discussed in my earlier video elaborately. Now I will see number of prime ideal of this ring R. For I1, consider two element 1 0 0 and 0 0 1. Then their product obviously belongs to I1, but neither 1 0 0 belongs to I1 nor 0 0 1 belongs to I1. So I1 not be a prime ideal. Similarly for I2, consider two element 1 0 0 and 0 1 0 from the ring. Then their product 1 0 0 0 1 0 be the member of I2. Just notice I2. Consider here the member of Q equal to 0, but neither 1 0 0 belongs to I2 nor 0 1 0 not belongs to I2. Similarly, for I3, here notice I3. For I3, consider 1 0 0 and 0 1 0. Then their product belongs to I3, but 1 0 0 not be member of I3. Similarly, not be member of I3. 0 1 0 not be member of I3. So this ideal is not also prime ideal. For I4, consider 0 0 1 and 0 1 0 belongs to I4, but neither 0 0 1 belongs to I4 nor 0 1 0 belongs to I4. So I4 also not be prime ideal. Only prime ideal be I5, I6 and I7, because whole ring not be prime ideal. And this is be prime ideal as same like Q cross C. That means this ring R has 3 prime ideal. Are you getting? Well, we'll see some very important topic about prime ideal. And this topic is very important for any competitive exam and for deep knowledge in ring theory. We all of us know about integral domain. All of us know if R be a ring, then R is called integral domain if AB belongs to R and if their product equal to 0, that imply obviously either A equal to 0 or B equal to 0. We all of us know this is the definition of integral domain. If R be integral domain, then obviously always the zero ideal be prime ideal. Because if A and B belongs to zero ideal, then obviously either A equal to 0 or B equal to 0. So, zero ideal obviously be prime ideal when the ring is integral domain. As for example, if we consider the ring equal to Zi, rational number, real number C, Z, P, Z, R cross 0, then obviously those ring are integral domain. So, I equal to 0 be here for this ring prime ideal. There exists a very important theorem. R is a commutative ring with identity, then P subset of R is prime ideal if and only if the quotient ring R mod P is an integral domain. This condition is if and only if condition. If you know the theorem, then it will be so easy to find integral domain. Let's see the proof. Consider P is prime ideal and we have to prove R mod P is an integral domain. For this, consider two zero divisor in the quotient ring R mod P. Consider A plus P times B plus P equal to 0 plus P, which is obviously belongs to R mod P. By the rules of quotient ring, this would be AB plus P, which is equal to 0 plus P. And when two quotient are equal, then we can tell easily from this line AB belongs to P. And since I have considered P is a prime ideal, then by the definition of prime ideal, this means either A belongs to P or B belongs to P. Then from this line we can tell A plus P equal to 0 plus P or B plus P equal to 0 plus P. Therefore, just look, from this line I have got either A plus P equal to 0 plus P or B plus P equal to 0 plus P. That means obviously R mod P is an integral domain. Okay? Well. Conversely, suppose R mod P is an integral domain and we have to prove P is an prime ideal. Then consider AB belongs to P to prove prime ideal. Then we can write AB plus P equal to 0 plus P since AB belongs to P, which belongs to R mod P. And AB plus P means by the rules of quotient ring, this is equal to A plus P times B plus P, which is equal to 0 plus P. And since R mod P is an integral domain, therefore we can tell easily from this line either A plus P equal to 0 plus P or B plus P equal to 0 plus P. That means from this line either A belongs to P or B belongs to P. Therefore, I have considered AB belongs to P, and I have got either A belongs to B or B belongs to P. That means P is obviously prime ideal. Therefore, our proof has done. Okay, now I will see how this theorem is very important to find the prime ideal. In my previous video, I had seen in QX, ideal generated by X is a prime ideal. In my earlier video, I had proved it by definition of prime ideal, but now I will use this theorem. Here we have to prove R mod P is an integral domain. That means here we have to use just first ring isomorphism theorem. Just notice, in first isomorphism theorem, I had defined the map Qx to Q, and the mapping, this mapping is evaluation mapping. So here the mapping is defined as f of x maps to f of 0. This mapping always be ring homomorphism, and I had seen here the kernel of f would be the ideal generated by x. That means all polynomial whose constant term is 0. So by first isomorphism theorem, we can tell Qx modulo ideal generated by x is isomorphic to Q. Therefore, R mod P is isomorphic to Q, and since Q is an integral domain, so by this theorem we can tell ideal generated by x in Qx be prime ideal. Are you getting why this theorem is very important for any competitive exam? Because if you know the theorem, then to find the prime ideal, it will be more easier than the definition. Okay, well. Similarly, we can tell in Zx ideal generated by x or ideal generated by x minus 2x minus 3 so on will be prime ideal, which I had seen in my earlier video. But by this theorem, Zx modulo ideal generated by x minus 2 would be isomorphic to integer, and since integer is integral domain, so we can tell this ideal is prime ideal. Okay, well. Now consider CXY and consider a ideal generated by x and y. This is actually polynomial with two variables x and y. And in CXY, we can construct a ring homomorphism CXY modulo ideal is isomorphic to C as like F map to F00. This is the evaluation map which I had discussed in my previous video. Are you getting why my previous video is very important? I will highly recommend you, if you don't see my previous video, then at first see my previous video. Then this topic would be so easier to understand in better way. This is just evaluation map. And in 6CXY, ideal generated by x is a prime ideal. Why? All of us know we can write CXY is as like This is the polynomial with variable x whose coefficient is 1. This term also I had defined in my earlier video. And then we can write Cxy modulo ideal generated by x is equal to Cy x modulo ideal generated by x, which would be isomorphic to Cy. Are you getting this mapping? And this is the integral domain because this is the polynomial ring whose coefficient y be the member of complex number. And Cy is an integral domain because if R is an integral domain, then obviously Rx will be integral domain. Because if we consider two polynomials in Rx such that both are non-zero, then their product must be non-zero. And this is true because consider two non-zero polynomial fx of degree n and gx of degree m, where an and bm not equal to 0. Here an and bm just coefficient of n and coefficient of m, such that n belongs to real number and bm belongs to real number. Since R is an integral domain, that means if an and bm be non-zero, then their product must be not equal to 0 because R is an integral domain. And since an bm not equal to 0, then product of these two polynomials would be an bm times x to the power n plus m plus up to dot dot dot. This is the lower degree term of this polynomial and this is the highest term of this polynomial. Since the largest term of this polynomial is not equal to 0, so we can tell easily fx gx not equal to 0. And this is true only for R is an integral domain. So our proof is done. If R is an integral domain, then obviously Rx is an integral domain. Let's come back our previous example. Here Cy is integral domain because the complex number is always integral domain. Okay, are you getting? Well, and this type of example is very important for any competitive exam, NET, GATE, all type of exam. Today I will stop here, but I will highly recommend to you, please see this video with pay attention because this video is very important for any competitive exam. Soon, stay safe and stay positive always. And don't forget to do subscribe my channel and press like button. Thank you so much.